So now we're going to be looking at concavity and the interpretation of the second derivative. And in general, concavity is kind of the physical interpretation is when the second derivative is positive, we say it's concave up. It looks like this, like a bowl facing upward. And when the function has a second derivative less than 0, it's concave downward, or it's bowl facing downward. Okay, so that's what we're doing. Kind of like the first derivative tells you when a function is increasing, it's ramping up or going downward because the slopes are positive or negative. Concavity doesn't tell you whether it's increasing. It's telling you whether it's bowl upward or bowl downward. So if I have a curve like this, for example, in this area it's concave up, here it's concave down, here it's concave up, here it's concave down. Now, points of inflection are the points where the concavity changes. So, like, for example, on a curve like this, around here, the curve kind of went from concave up to concave down. And then around here, it went from concave down to concave up. See that? So those would be kind of the points of inflection. And maybe another one right here, if I were to extend this, and this was concave down and concave up. Those would be the points of inflection. Points of inflection are where the second derivative equals 0, and the concavity changes between the left and the right point. So kind of like when we were using the first derivative test to find mins and maxes, where a min and a max is where here's a minimum, here's a maximum. It's kind of like I made a number line or an interval where I said to the left it was positive and to the right's negative, or it went from negative to positive. If I'm looking for a sign change, that means the concavity is changing, and hence that is a point of inflection. So that's kind of the logical process we want to take through when we're doing this. So A is find the points of inflection, and then find where the function is concave up and down. You can do these both together by this kind of method. We're going to compute this second derivative, but first we need to compute the first derivative. That's equal to 2x minus 2. Then we need to compute the second derivative. Second derivative is just equal to 2. Okay, so this function is never equal to 0, so there's no points of inflection. And the second derivative, by being 2, it's always greater than 0. Always. So it's only concave up, and it's always concave up. Concave up. And if you think about what this is a graph of, this is a parabola, an upward-facing parabola. And it should make sense that it's concave up everywhere. It never looks like a bowl downward for this graph, right? And so that's what analytically we have found. Okay, let's look at this one. First derivative is 3x squared minus 1. Second derivative is 6x. Okay, now sometimes this is going to be positive, sometimes it's going to be negative. The transition point is when it's equal to 0, so that's x equal to 0. So x equal to 0, the second derivative is definitely equal to 0. And so we make kind of a little line like this where I say, well, at 0, definitely the second derivative is 0. When x is less than 0, or x is greater than 0. So x is less than 0, what is the second derivative doing? Well, when x is less than 0, this value is going to be negative, right? Because if I do like -1, for example, it's going to be -6. And when it's greater than 0, when x is positive, this whole term is positive, okay? So x equals 0 is a point of inflection. So this is a point of inflection, because the concavity changed. See, it changed from concave down to concave up. Okay, this is concave up, this is concave down, because when the second derivative is negative, it's concave down, this is concave up. So in this interval, it's concave up, and this is concave down. Okay. So find the critical numbers for the following functions and use the second derivative test to classify as a min, max, or neither. Okay, so this is a different way of finding mins and maxes. Is we simply find our critical numbers for this is again back to the first derivative, because I'm trying to determine whether I have mins or maxes. And so if I draw a picture of a min or a max, in both cases the derivative is 0 or undefined. Those are my critical numbers. But rather than doing a sign test, which is whether or not it goes from positive to negative or negative to positive, if I can look at the second derivative and say, like, well, if it's concave down and it's a critical number, it must be a maximum. And if it's a critical number and it's concave up, then it's a minimum. Okay, so first I want to find critical numbers. That's where the first derivative is 0. That's 2x minus 2. It's equal to 0. That happens at x equals 1. Okay, and then rather than doing a sign test, like we would do for a first derivative test, I compute the second derivative, and that's just equal to 2. Okay, so it's always concave up, x equals 1. And so which picture does that look like? Well, the slope is 0 here, and the second derivative is positive here, right? Because concave up is second derivative is positive. So x equals 1 is a minimum. And that should make sense to you because this is a upward-facing parabola. So, I mean, that would be the minimum. So I actually do remember, I think these problems are identical to actually the previous sets of problems, I guess. But you could do a first derivative test on these, and you would find the same thing. Okay, so first derivative of x. To find the critical numbers, I want the first derivative 0. That's when I'm trying to find mins and maxes, right? 3x squared minus 1, when that's equal to 0. So that means 3x squared is equal to 1. X squared is equal to 1/3. X is equal to plus or minus root 1 over 3. That's equal to plus or minus root 3 over 3. Just to rationalize the denominator, if you wanted to just do that. Okay, so I have those two possibilities. So I have x is equal to positive root 3 over 3 and negative root 3 over 3. So now I need to compute the second derivative. Second derivative would be 6x. Okay. And so when I plug in positive root 3 over 3, it's greater than 0, so it's concave up. And when I plug in negative root 3 over 3, when I plug in a negative number here, this whole thing's negative, right? So this is concave down. And remember, I drew my picture. When it's concave up, like this, then that makes this a x equals root 3 over 3 is a minimum because it's concave up. And x equals negative root 3 over 3 is the opposite because it's concave down. It looks like that. And this is what concave down looks like, negatives. So this is a maximum. Okay, so that's how you use a second derivative test. I simply look at, I classify my critical numbers by simply looking at whether it's concave up or concave down. Now, if the second derivative is 0, it's inconclusive. The test tells you nothing about it because you cannot use the concavity for whatever reason to classify that point. And that does happen sometimes. Thanks for watching. If you're looking for more examples, go to my website. In there, I have free access to over 400 calculus questions that I solve and I show you step by step. So if you're interested in seeing more, please check out my website.